attending any conference, it's incredibly important to be there. That's kind of the only way to really dedicate your time to be there and kind of be immersed in the whole thing and not distracted by other stuff going on, even if you do get distracted with interesting conversations in the hallway.
Hello, everyone. Welcome. First things first, I just want to say that I prefer to take questions at the end, but if there's something urgent or a correction or clarification or something, you can interrupt me. That's totally fine. So my name is Jacob Rice. Let's get the theme fixed there. I work at Keysight Technologies, so thank you to Michael for the great shout out at the plenary. If you're watching online and you haven't seen it, small inspiration. It's a great talk. So I really like writing library code. I think that's true about a lot of people. There's a lot of satisfaction that you can get out of writing that really nice, reusable code. But that's not the kind of code that I write all the time, right? And that's what I mean by the rest of us. There are these library features that are kind of opaque and kind of hard to understand if you just look at them. But I want to prove that views aren't one of those, and I'll talk about views in a moment here. So my goal whenever I talk or teach is to build an intuition, okay? Memorization is okay, you can get into technical detail, and that's fine, but I think that most of the time you end up having to go back to the documents anyway. So what I'm trying to get here is an intuitive understanding so that everyone kind of has the same level of understanding of what views are. If you don't know about views, this talk isn't really intended as an introduction, but I hope that you nevertheless are quite familiar with them. They offer this clean, composable, lazily evaluated syntax for writing common algorithms in C++20. And when you first see them, they can seem a little bit magical. They have a totally different syntax than anything else in the language. There are like 1,000 different ways of using them. So it's weird to call them clean, but generally the best way to use them is very clean. To make it a little bit clearer, I tried implementing one myself, and I want to share that process with you. So let's start with the motivating example. This is a little solar system simulator that I was working on in the Unreal Engine. In order to calculate all of these orbits, I first had to calculate the forces that every planet or the sun was exerting on every other planet. So let's take things down one dimension first in order to reason about this a little easier. In general, this is 2 planets and a sun, so in the context of calculating the forces of gravity, I'm going to call these gravitational bodies. So I have a concept here which expresses what I require of that type. If you're not familiar with concept syntax, just trust me that it's okay. I'm essentially saying that my type has to have get mass, get location, and get velocity, which all return the types that work for the concepts on the right-hand side. Then I also have a concept called gravitational range, which is just my way of expressing a function of gravitational bodies. So in order to calculate the force of gravity, I first need to go through every planet, and for each one, or gravitational body, for each one I then need to go through all the others and see what force each of those is exerting on the one that we're looking at. And then I can return a sum of all of those vectors, right? And that gets the total force exerted on this one. So a first pass at that algorithm in pseudocode or in Python code, because they're the same thing, is in the inner loop, we're going to pass in the planet that we're looking at, which is the red planet in that example, and then a collection of all of them. Then we loop through all of them, somehow calculate the force that each one is exerting on the current one, and then add that to a list and return a sum. If you know your standard algorithms, you may see that this can be done as a transform reduce. So that's actually how I'm going to implement it. So this is the somewhat more verbose C++ code version of that, including a definition for that calculation. And at the bottom, we can see that I do a transform reduce. This is a custom version that doesn't require passing begin and end. And the transform operation takes an individual body and turns it into a floating point vector. So this is a mathematical vector, not a std vector. But when it runs into the current body that we're looking at, it just says, it returns 0, right? The red planet doesn't exert a force on itself. Otherwise, it does an actual calculation using Newton's laws of gravitation, which we don't have to worry about right now. So overall, this works really nicely. Like, it's really fast. It can be optimized really well. But this line is a little bit smelly to me, because this tells me that the input data into my algorithm is wrong. If my algorithm had the correct data, then it wouldn't have to correct that data, which is what we're doing here. We're saying that we don't want to consider a planet exerting a force on itself. We're doing a Cartesian product, looping over every planet. Inside of that loop, we are again looping over every planet. But then we're throwing out the pairs of matching elements, the diagonal in the Cartesian product, right? This is the wrong input data to the algorithm. The algorithm should really just be calculating a force. It shouldn't have to do this. What I would like to do is take my gravitational bodies and view them as groups of pairs, where everything is just paired with the stuff that exerts a force on it. I could generate that thing on the right and store it in a vector, a std vector, but that would take a really long time to generate. It would take a lot of RAM because it grows by n squared. That's not a good solution. So instead, I want to view my algorithm, my data like this in the algorithm, but I want to do it in a way that doesn't run out of RAM. And I can achieve that with a C++20 view. So first things first, what is a view? Note that I will be using the std_views namespace. This is easier to access, but it is a sub-namespace of the ranges namespace. So let's disambiguate some terms which are often used close to each other in these talks. A range isn't a new thing in C++20. It's just a formalization of an old thing, right? It's something that has begin and end function. Semantically, it's some collection of stuff. That's all it is, right? It's a generalization. A view is a specific type of range, and while the requirements in the standard are specific, I'm not going to get into them because they're overly specific for a useful model. So mostly, a view can be defined as just a range which can be used in a range adapter pipeline. That's the definition I'll go over next. There are a bunch of requirements for the amount of time that it takes to use a view. So constant time move construction is one of those things. If it's copyable, then it must be constant time copyable. Though there are some requirements on destruction, but all of those are kind of too in the details. There's also this const per Boolean that you can opt into and say, my type satisfies all of those things, because the compiler can't see whether it's constant time move constructible, right? So range adapter pipeline, this is a composition of range transformations that evaluates lazily as the resulting view is iterated. So this is a somewhat recursive definition with view, where they both require each other in order to be defined. But we press on, it's okay. So the important thing about a pipeline is that it's really cheap to create, right? It doesn't do any work on construction. It just does all of the real work as you iterate over it. Okay, this is the thing that we saw here. So when we construct iota, pipe filter, pipe transform, it's very cheap to create, and all of the work where we generate an integer, decide whether that satisfies the even lambda, and then transform it into the square of itself, that all happens during iteration. Another couple of terms that you might see near each other in discussions of ranges, especially of views, are range adapter and range factory. So I will be focusing on range adapter. This is a type of view which has some kind of backing range and represents it in a different way. This is what we call adapting. The case with most of the views in the standard. Ref view takes another range and just represents it as pointers. It's forward, it's one-to-one. Filter view represents it by pretending something is in there or isn't by doing a filter with the lambda. Range factory is a view which more or less generates elements on demand. It provides elements on demand, but it doesn't necessarily have a backing range. So these are things like iota view, which creates integers as you request them. This is single pass. You can't go back because it just is creating integers and incrementing. iStream view allows you to iterate over words in an iStream. And then there's also single view and empty view, which aren't terribly interesting. A little bit more terminology. We're doing this in 2 for loops. We're doing a nested for loop. So I'm going to refer to that bracketed section as the inner view because we're doing it in the inner loop, and then iteration across that as the outer iterator. So here is a high-level description of the view. I would initially like to say that this is not a production-ready view. This is merely a slide-ready view. There are some use cases and test cases which I don't account for because it adds a whole bunch of detail to slides, and I'll talk about some of those as we encounter them. But the first thing I want to take a look at is the template signature. So this is the case with most of the range adapters in the standard. They're templatized on essentially what was piped into them. So this all pairs view receives some kind of view, not just a range, it's always a view. It requires at least a forward range of that view because it needs to do multi-pass, so it can't be an input range. And then it inherits from view interface, which gives us a couple of things, including that enable view const expert Boolean. So this line right here is hiding almost all the detail, but this makes sense, right? Because we know that views are easy to construct, but hard to iterate. So all of the interesting stuff is happening inside of the iterator. So we can break out our types a little bit in order to make them a little easier to investigate. And we can take a look first at the constructor. So you can see that I have one member variable, which is just the view that was piped into this one. And we just take it by value and move it in. It's pretty straightforward. This deduction guide is there for all of the range adapters, maybe all of the range adapters. This essentially says, this allows us to pipe a vector straight into our view, and the machinery can automatically wrap that vector in another view. Okay, that's really all that we can look at now, but more later if you're curious. So then into the iterator types where things start to get interesting. So here I define a bunch of types, and remember that tbase is the thing that was piped into this one. So the value type of this iterator is a pair of the base value type because I'm providing, say, pairs of planets. The reference type is a pair of base references. This kind of makes sense, although it's a weird reference type, and we'll come back to it. I'm also only doing a forward iterator for slide code reasons, mostly, but it should be enough to get the point across. The other thing that I want to note is I'm only defining 4 types here for an iterator. You may be used to, before C++20, if you've ever written one, you had to define 5 types, these 4 plus pointer. As of C++20, you don't have to define pointer if it doesn't make sense for your type, which is kind of a nice thing. There are ways that we could provide a pointer, because without a pointer, you can't have an arrow operator, but I'm just skipping it for now. You can look into arrow proxy if you care. So then here are the members. I have 2 component iterators, which are outer and inner. They could be called first and second in my pair, and a pointer to base, which I'll use later. And then I have one little bit of business logic. So this is the code that I didn't like before. This is where we ignore pairs of matching elements. Okay, so this isn't the best implementation maybe. There are a lot of ways of implementing it, but this is how I chose to do it for the slides. Then we can move on to the constructor and the dereference operator. So the constructor, there's always a default and a useful one. And then we make sure that our inner iterator is valid. And then our dereference operator just returns a pair. These are the component iterators that we had. Increment operators, prefix and postfix, also straightforward. Postfix is always in terms of prefix. I like to mark it no discard because if you're using this but not saving the value, it's just a waste of time. Or compiler. And then equality operator. That's all there is to it. As of C++20, we get operator not equal auto-generated for us for free, which is a really nice effect. So the next thing to look at is the inner sentinel. And because this is kind of a new thing. We all know what sentinel values are, right? We know about the null character, which is the same type as the rest of the range, but it tells you that you've reached the end. A sentinel type is a new thing in C++20 because sentinel values don't work for a lot of types. You can't have a sentinel integer. So this is a different type returned by end than by begin, and its job is just checking with the iterator type. Okay. And the important part about that job is that if an iterator isn't equal to its sentinel, then that iterator is dereferenceable and incrementable. So it's still valid. So this tells us that once it is equal, you've reached the end of the range. There's also a concept for it. S is a sentinel for I if S is copyable and default constructible. I is some form of iterator. And then there's an equality operator, which we already looked at. Okay, so here is the actual inner sentinel. It's very straightforward. That first method where sentinel is equal to true all the time is kind of a convention to complete a truth table. It's not terribly interesting, but that operation shouldn't really get you anything interesting. But we like to make it valid. I don't know. Not sure if I'm on board with it, but it is a convention. And then we have the useful equality operator, where we just see if the iterator is equal to the end of the range. As of C++20, that method not only generates the not equal operator for you, but also the arguments reversed. So even better. You don't have to do 4 free functions anymore for that kind of thing. But why use Sentinel at all? End iterators have been around for a long time. They do a lot of work. Why not just use one of those? I'm going to brush over this a little bit. I'm going to show you why, but it is a little bit specific. Our constructor only supports constructing the outer iterator. And that's fine, right? This is most of our use case. If we wanted to construct an end iterator, we'd have to be able to pass that in. So we could add a constructor overload, and that would be okay, where we have current inner, and then we save that one. But should we correct that? If it's pointing at the pairs of matching elements, you would hope that no one passes us pairs of matching elements. But I've written code. I know that people use interfaces wrong. So we should probably try to recover. But I don't know, there's something weird about this, because this should only be used by the call to end, right? That's the only one that should be using this, but there's nothing that enforces that. So really the point of using sentinels is that they separate concerns. You can just put all of the logic for end in its own class, and you don't have to worry about it polluting your interface for your iterator. So I really like reading sentinel code. Highly recommended. Okay. So the inner view this is the whole definition. That's technically a view. There's really nothing interesting about this. It just provides the iterator and sentinel pair. And so we've technically done our job. We've made a view, but we're not quite done because we have the outer iterator. So this is where things really get interesting. You can see our 4 types that we're again defining, and we have reference equals value type. That's not a reference type. That's a little bit weird. I'll come back to that. We can just look at the constructors. Dereference operator is going to create an inner view. So when you're iterating it and you dereference it, you get a new inner view. And then increment and equality, just like the last one. So why is this not value type ref or value type const ref or whatever? Well, the problem is, on dereference, I'm creating an inner view. Where should that inner view live, right? An iterator isn't really supposed to own the data that it's pointing at. That's not the job of an iterator. So I have it just creating this R value here. But is that a good idea? I don't know. So in order to investigate this weird reference type, as well as the inner iterator reference type, which is also not a reference type, it's a pair of reference types, we need to take a step back into a much older problem that I think people here are probably familiar with, vector of Bool. And specifically what C++20 fixes about vector of Bool, because there's a lot. So first the problem, right? Vector of Bool is more space efficient. Hopefully you can see that. Because it doesn't necessarily store its elements as a contiguous, and it exposes a class called vector Bool reference as a method of accessing individual bits. So what this means is instead of storing 7/8 wasted space, we pack everything together as individual bits, and then look at that, we have another half of a byte before we need to ask for a new one. So I'm not here to argue whether this is the right thing to do or whether you should use bit set, but there are arguments for that. But one of the problems is instead of having a nice type table where you can tell like const reference is const value type ref for a normal vector, vector of Bool is almost all implementation defined, right? Everything is hidden from the user. The const reference is just a Boolean by value. That's not a reference type. But the one that I really want to look at is the proxy class representing a reference to a single bool that it uses for its reference type. So this has been talked about a lot, including a great article in 1999 by Herb Sutter. And in that article, he shows this example, right? You have a function template which takes a t, takes the 0th element of t, and then takes the address of that. This seems like perfectly good code. This compiles. This would work correctly for a vector of int because there is an integer in memory that you can take the address of. But a Boolean, as we saw, it's actually just a bit. There's nothing to take the address of. So this would break at runtime. So what do we do about this? Now, there are a lot of rules in C++ like don't write code like this, but those are not memorable rules. If you just have a laundry list of things that you should avoid, you end up with code like this. So a more general rule would be write code expecting proxies, which I'm going to talk about in a moment. But this actually falls under a wider umbrella of rules now, because we can just write code that conforms with C++20, and we'll be okay. If you want to know more about proxies, you can read the original paper where Eric Niebler introduced proxies into the standard. So, a proxy reference. This is just a type which provides read and write operations for another type, even when it's an R value. And that second use of type is a little bit off because the vector of Bool reference, proxy reference type, provides read and write operations to an individual bit, which isn't a type, but that's okay. More useful for our purposes is Proxy Iterator, which is just an iterator whose reference type is a proxy. So we've seen some examples of this. Obviously, vector of Bool iterator. Dereferencing that returns an R value of type reference. This is a class. And that provides you with the read and write operation you expect. The all pairs view inner iterator, dereferencing that one returns an R value of type pair, right? Or of L value references. So seeing this kind of thing might make you wonder, are these even allowed? Because this is really weird behavior. You expect references to be references. The answer is yes, but again, only as of recently. See, the problem was before we had this named requirement called legacy forward iterator. Here I express it as a concept, and there's a lot going on here. But the important thing to see is the reference type of the iterator had to be a real L value reference. That was a requirement before. Nowadays, though, we don't have that requirement. It's a lot easier to be a forward iterator. Okay? So that's a good fix. What this means is vector of Bool's iterator didn't even count as a forward iterator. Okay? It, I believe, did count as an input, but we expected it to be random access, so that's a little bit weird. Nowadays, you actually get to support the type, and vector of Bool is fixed. We'll call it fixed because this behavior is fixed, so for our purposes, it's okay. I'm getting a no. Definitely not fixed. So what else is required for these proxy iterators to work? Because that wasn't everything. The first thing I want to talk about is the customization point object. You may have seen these referred to as Niebloids, named after Eric Niebler. These weren't strictly required for behavior, but this is a useful pattern to understand for the rest of our requirements. So we've had this pattern for a really long time. In your generic code, you take two t's and you use std swap and then you swap them. Okay? This is a pain. If you didn't know you had to do this, or you don't know why, you're not alone. I've seen this messed up a lot, right? The reason you had to do this was because swap, along with begin and end, although those two less so, they were all customization points. So a user can define a type for which this function doesn't behave the same way, doesn't work. So they can define their own version of this in their own namespace. And then we have to let the compiler find that version, right? We use argument-dependent lookup for that. I'm not going to get into it. This is a pain. So the solution now is to use a particular object that does this trick for you internally. As an added side effect of that, a benefit of that, we now have one place to constrain because we have one call site that everyone uses, so we can add concepts and make sure that the types passed in actually work and make sense. The only ones that I know of are in the std_ranges namespace right now, but I'm expecting that this will spread into other parts of the standard library. Maybe not. So now this is how we can swap stuff. So it might seem a little bit weird to use std_ranges swap if you're not using ranges, but it does work. But this is just an more memorable way of writing stuff. Of course, we have to leave std swap alone. We can't change its behavior. It's still there. This will find the custom versions that you expect. Okay, with that in mind, we can now look at iterswap and intermove. So say I had this, in this case, this isn't just bad slide code. This is actually implemented as std, but I want to swap the contents of two iterators. So I take them by value, I use std swap, and then I dereference and swap those. Seems like I'm doing everything right, and that is true. This works, except now that we're trying to support proxy iterators, it doesn't. If dereferencing returned 2R values, then swapping them just swapped 2R values, right? And our original container is still the same. So this doesn't work. So std_ranges iterswap to the rescue. This is designed for proxy iterators. It's an improvement on std iterswap. And all of the std_ranges algorithms that need to swap things in a container will use this. If you are also swapping things in a container in generic code, you should also use this. This is the right thing to do now. If you are writing your own iterator, you don't have to customize this. You can just do Intermove, which is what we'll look at next. So this is an example of bad slide code, but I want to extract a value from an iterator, maybe leave it pointing at nothing, and I'll fill it later. So I, pass it in, dereference it, return that. This would more correctly be iter r value reference t, but I didn't want to get into that. And this worked perfectly fine, except that now we support proxy iterators. You might have moved an R value, which was useless, and your code is broken again. So Intermove to the rescue. This didn't exist before. There was no std Intermove before, which was arguably an oversight. And this is, again, used by all the std_ranges algorithms that need to move values out of containers or iterators. So this is also what you should use. If you are writing your own iterator, you can customize this, and customizing this will give you iterswap for free. So as a side note, this is another benefit of using that sentinel type. So if your begin and end don't return the same thing, they won't be able to work with standard algorithms. You would have to use the std_ranges algorithms. Standard algorithms still have the same broken behavior for proxy iterators. So those algorithms wouldn't work with a proxy container. So if you also use a sentinel, you can make sure that that won't compile. There's an asterisk because you could use common view to fix this, but it would then be broken. It takes work to get around that problem. So sentinels are a nice way of reminding people that your iterator needs to be used in ranges. Okay, so what does it mean to customize Intermove, right? You can look up the overlay solution rules for it, but this is intentionally small. It's not easy to read if you're just trying to figure out how to implement it. So let's make it simple. Define a function in the namespace of your iterator that takes your iterator and does the right thing. Otherwise, it'll just do the normal dereference and std_move. Okay? Simple as that. So here's an example of doing that. And I want to put a pin in this because this example doesn't actually work for my iterator type. It looks like it would, correct, but there's a reason that it won't work for my iterator. So don't actually implement it like this, but I'll show you why. This is a perfectly valid way of doing it. If you're okay with template argument deduction, we can make it nicer on the slide. But that's all. It's a constacks per friend function, takes the iterator, and then intermoves the component iterators that I have in there. Okay? And that seems to work correctly. Except, if you think about what intermove is supposed to do, it's supposed to move a value out of an iterator. So we have a container. we want to do this, but my implementation did this. I invalidated my entire container. That's not good. So this is a problem that if you're writing an iterator that exposes elements multiple times, you can't really intermove out of it. I don't know of any way for that to work other than just creating copies of the things, which seems like a really bad idea. So don't do that. Okay. The last piece of the puzzle is stood common reference. So this is a tricky one to describe, and I tried it once and I didn't do a good job. So I reached out to Eric Niebler for some advice on how to describe this, because there's not a lot of documentation online. And I got some useful advice that I wanted to share. So I'm going to skip it. It actually isn't worth the amount of time. It's probably a talk on its own. For the most part, I don't recommend customizing this, okay? But for an iterator that's, for example, providing a pair of L-value references, you need a customization. So I recommend finding an example online. Here are some links for you that would be helpful if you wanted to customize this. P2321 has implementations for tuple and for pair, and so that's probably sufficient for you. But this is a tricky feature to use. So this is not a good one to teach in a kind of introductory talk. So there's also an interesting topic or post on Stack Overflow that I linked there, which is the use in equality comparable to and a whole application of this. So that's all I can give you. With that, we can go back to the solar system simulator and the all pairs view. That's the end of the outer iterator. Okay. And then the only thing that remains is begin and end. So there's nothing interesting here. We already saw the iterator type, so we're just constructing those. Here I'm not using Extensional. I could have, but this one already had a constructor overload that worked, so I can just use the end iterator for it. And this is good enough. So nothing that I showed here explains the piping operator. So that's what I want to take a look at next. Unfortunately, the piping operator isn't customizable. So this is a sad finding when you're writing a talk about how to customize. This is almost certainly going to get fixed in C++23. It's not fixed yet. But we can still take a look at how it works, right? This is a high priority to get fixed. So the first thing I want to do is take a look at a common use of ranges, or of views. Often in our code, we like to compose things together first, and then name that something useful for us. If you want to see an interesting application of this, you can see Tristan Brindle's talk from last year's CppCon, where he did string trimming with views. It was very handy. And then we later use that better named version in our code. And we actually provide it with data and then use the view for something. Okay. So let's take a deeper look at this line here. Let's go over a couple of things about this line that I think everyone needs to be on board and have the same kind of idea of how it works. So we're using stood views reverse to create a reverse view. That is the view type. Reverse isn't a view. The standard is hazy about whether it's a range adapter or not. Range adapter isn't really that specific to whether it applies to the view or to the thing that creates a view. It's a little weird. But this is analogous to the all pairs view that we've looked at. Okay. So stood views filter does the same thing for a filter view. If you look at the CPP reference for them, you'll see that reverse view takes a range and represents it in a different way. We need to do something with the mic. Okay. And then filter view takes a range and also a function, and then how's that? Better? Okay. So filter view needs 2 arguments to be constructed, and reverse view only needs 1. Okay. This is an interesting property that we will look at. Another thing about these is that you may know reverse can be used directly in a pipeline, but filter can't be used in a pipeline until you give it that second parameter. Okay, this is what we saw here, right? We can use reverse directly in the pipeline, but filter doesn't really make sense until we know what we're filtering on. So with that, I want to then look at a little bit of standard ease because there isn't a common way of defining this. The first thing that I want to look at is the range adapter closure object. So this is a catchy name. I might call it a closure object just to be easier to say. But a closure object in this context is a unary function object that accepts a viewable range argument and returns a view. So a viewable range is essentially a way that we describe a range which it is safe to convert to a view. It's changed a little bit recently, but I'm not going to get too much into the details of that. It's just a range that we can view. Given a closure object C and a range adapter R, these two things are the same. So this is a weird thing. This is the magic of it. It's a unary function that you don't have to pass the argument in. You can pipe the argument in. And that's bizarre, but that's the closure object for you. Given another closure object D, composing them together gives you another closure object, which we can call E. And then I'm going to simplify because the details of move semantics and how they express this is a little bit more complex, but these things are all essentially equivalent. So this is the composition. Once you compose C and D, it's the same as passing your range to the composed versions. So the second definition is the range adapter object, frighteningly close to the first definition that we looked at. But this is also a function-like object, and it accepts a viewable range as its first argument and returns a view. So this is a more general case of the closure object, right? And indeed, if it only accepts one argument, then it's a closure object. So if it accepts multiple arguments, and again, I'm going to simplify here, the important thing is that passing the additional arguments to it gives you another closure object. So we have seen both of these things here. Reverse is a range adapter closure object. Filter is a range adapter object, which we gave its additional parameter. We composed those two closure objects and got another one, and then we used that closure object later, and that gives us a view. So why can't we customize this? There's not much of a reason except that it just didn't get named. So there's a type which we use for composing these two things, and that type is, there's one common type in all the implementations of ranges, but it's just not specified what the name of that type is. So we can't use it. I'm not blaming anyone for this. I mean, we've seen a tiny fraction of a tiny portion of C++20. There's a limit to how much you can put in a standard. So this is one of the things that just didn't make it in time. But if we wanted to do it, we could. This is a really bad thing that I'm doing. But this is the MSVC private type that you're not supposed to be able to touch. But I mean, you can. It's in a header. So obviously don't do this, right? So before we look at that, the proposal is to call that type range adapter closure and just use that, okay? I mean, there's more to it than that. It needs to be specified more. But this is what C++23 code will probably look like. Okay, so this is the answer. You could replace this with the equivalent in range v3. If you were using range v3, that would be fine because that is part of the public interface, I believe. But so this is the C++23 code. And this would get us bought into the pipelines, okay? So the first thing that we see is a concept. I don't know if this has a name, this pattern, but I like to call this a deferring concept. Essentially, this says that as long as T satisfies whatever constraints all pairs view uses in its constructor, then T works in this case as well. So this lets us avoid repeating concepts and the requirements on our types. So then we have our range adapter closure type. And we are, again, using CRTP, that's common in here. We only have to provide a parentheses operator. This accepts a viewable range, and then as long as it is valid for all pairs view, and then forwards it into all pairs view, which uses the constructor that we saw. This is where it invokes that deduction guide and wraps the range if it needs to. So the last part is just to name that and use it publicly. So this is the thing that you would use in a pipeline, and you're good to go. Okay, so in conclusion, all pairs view showed that while views are sometimes tricky to write, it is really easy to use them. And all pairs view was a pretty difficult view in comparison to something like reverse, right? We're doing a two-dimensional loop. So while C++20 isn't quite ready for custom views, you can probably use range v3 if you want to do that. You can write a custom view, but you can't use it in a pipeline, which is the best part. Proxies are a problem. They're unintuitive, but they are valid, and they will probably break old code. Okay? There is a good chance that if you start using proxy types and you keep using old algorithms, something will break. So you have to be careful about this, right? There's this whole new world of new iterator types that we can use. And so you have to keep these in mind in your generic code and make sure you don't just use old generic code without considering this. Iterswap and Intermove showed how customization points are powerful, and while common reference isn't easy to customize, most of the others are. So these are important, and you should always use the std ranges algorithms if you can. So with that, that's all I have. Thank you. Yes.
So are you familiar with Boost STL interfaces?
Am I familiar with Boost STL interfaces? Yes, but I didn't look at what they provide for views. I would assume that they have something that makes this easier to write.
Well, so the main thing is all of the iterator mechanics that you have to write, which it's a sad presentation you just gave because it's so complicated to create a view that it's untouchable by most people. So
Yeah.
STL interfaces does that have, of course, you can't do the range adaptive closure.
Yeah, so the observation was that there was a huge amount of machinery that I had to write for those iterators, and so the STL interfaces make that a lot easier and more accessible.
It's a similar like CRTP design where if you do all the normal stuff, which you normally do, it'll just do those pieces and you only customize the stuff.
Yeah, it uses CRTP to customize everything. So you just have to specify a couple of types, and then it'll lay out all the rest of your stuff. Yeah, that's definitely an improvement, for sure. Online question? Oh.
If proxy iterators and references are so unintuitive and potentially breaking, what was the compelling reason to support them?
Good question. So proxy iterators are unintuitive and potentially breaking. Why did we support them? It's for views, essentially. So we have this way of representing data that we don't really own, and that means that we have an ownership problem because referencing means that that thing needs to be owned. And so in order to get things like views working, and there are a whole bunch more views coming in future versions, C++23, I'm not sure if zip view is going to make it in. Zip view is going to make it in, okay. Which that'll be interesting. I haven't actually looked at the proposal, but that must customize common reference. So all of these types are really, really nice and make our code really expressive, and so it was just decided that it's worth the cost. And most of the old code probably assumes that begin and end return the same type. So that could be a nice way of avoiding this problem, but it doesn't completely. Yeah.
There's another factor, which is the Sentinel allows you to create infinite range, which you cannot do.
Yeah. Yeah, the main reason that sentinels were added is that it allows you to create an infinite range. And so iota view, for example, if you don't give it an upper bound, it'll just keep giving you integers. And what do you return as the end then? You can't just make an iterator that points at the, I don't know, int 32 max or whatever. So you just return a sentinel which always says false, and then you can just keep going. So, yeah. Yeah, range factories tend to be a lot simpler, and you can just kind of fit them on one slide, and then that's all the interesting topics of conversation. But, okay. All right, thank you.